We are live.
So for the next 3 minutes, we will essentially be waiting for the audience to settle down. If you see the participant list below is started increasing. So that's basically the audience. So we give them typically 3 minutes for them to settle down before we start. This is to all the attendees who are logging in. We will be starting dot at 3 p.m. So we still have 2 minutes to go. One more minute before we start. So if anybody wants to keep any tea, coffee, or water besides them, we still have a minute to go. Ram, we have Vinistra trying to log in.
Okay. Just a minute, Kailash.
So we will start at 3. I'm sure he will log in by then. His session is not at the start, so we have some time for him to log in. So we are going live. 3, 2, 1. A very warm good afternoon to all the attendees and speakers from Mumbai, and a good morning to all our speakers from Netherlands. My name is Kailash Shirodkar, and I am the moderator for this session on Dutch answers to flood management that we have lined up for you today. I hope that we are all safe in this enraging pandemic, and while the world is facing this pandemic together, there's another crisis that's been brewing up over the last decade, and which will slowly, emerge as another big crisis that we will face, and that is the crisis of global warming and its impact on climate change. We all have been listening, and a lot has been written about global warming and its impact. And I think one of the biggest impacts that global warming would have is on rising ocean levels and the threat that it has to coastal cities spread across the globe. In a report that was published around 6 to 7 months back, it was mentioned that among the top cities that face a threat due to rising ocean sea levels, Mumbai was ranked number 2 as the city most vulnerable among India to the rising challenge of ocean sea levels. So what we have scheduled for the next 1.5 hours is to try to understand the impact that these rising ocean sea levels would have on a city like Mumbai, and try to find answers or solutions to them from experts or from a country like Netherlands that has been a pioneer and have actually done a lot of work in tackling this issue that faces most of the coastal cities today. So with that, I would like to invite Bart de Jong, the Consul General for the Netherlands Consulate, to deliver his opening remarks and specifically on how the country of Netherlands is facing this challenge. Over to you, Bart.
Thank you so much, Kailash, for that introduction, and welcome everybody to this webinar, Dutch Answers to Flood Management and Land Subsidence. A special welcome to Mr. Velros, who I would say is Additional Commissioner of the Mumbai Corporation, sorry, the Municipal Corporation of Greater Mumbai. I also have to find out what that abbreviation stands for. And of course, a special welcome also to all the staff of you, Mr. Velrasso, who's watching in various locations in Mumbai. The thing we're doing is an event in the framework of our Netherlands Meets Mumbai week. It's a yearly event. And we do that on the occasion of King's Day, and which was the 27th, and the 1st of May, which is Maharashtra Day. We did a series of events, and that explains a bit the festive mood I'm still in, celebrating the House of Orange, King's Day. That is why we all dress up in orange at the time. As you rightly said, Kailash, we're in the midst of a pandemic, and that is also the reason why we thought that we should cancel all the physical events. We had a number of live meetings planned in Mumbai. And we were actually also considering whether we should continue with the webinars we had organized. And we decided actually to do that because if there's one thing that the pandemic has shown in the last year, it is the value of connecting, connecting with each other through these kinds of webinars and electronic communications. So that's why we think it's important to still connect and still prepare physical cooperation for the future. Because like the COVID crisis, this other crisis that we're facing, climate change and the concomitant sea level rise, land subsidence, these are two urgent matters to delay action. So that is why we decided to continue. The models, climate models, sea level rise models actually show that among the cities most vulnerable to sea level rise, Mumbai is ranking number 2 in the world, most at risk of sea level rise. Beside that, there is this other issue that is caused by climate change, which is causing flooding, which is of course extreme rainfall and higher river discharges. Well, the Netherlands is actually sort of facing the same challenges as Mumbai in a way. And I have 2 slides to illustrate that. Ram, if you could put on the first slide. We are a country actually that, I don't see it yet, but I can start talking, keep on talking. We're a country actually that is for 1/3 below sea level. On the left, you see the blue area that is below sea level. And on the right, you see the bird's eye view looking over the cities of Rotterdam, The Hague, and Amsterdam, the 3 main cities in the Netherlands. And as I said, the blue areas is below sea level. And if you see in the next slide, what our country would look like if we hadn't done sea defenses for over 1,000 years, we've been doing that for over 1,000 years, the country would look like this. It would be flooded for 1/3 of the country. So that is an alarming notion, of course, but the thing is, it's not flooded. So that means that flood protection actually can work. And you're going to hear all about the way we've done that through the ages from various colleagues present here today. I think we can move back to the main screen again, Ram. So if you see that picture and you add to that that would actually the picture be if we didn't have any flood defenses. Climate change actually is exacerbating that problem, not only because of sea level rise, also because of the fact that we have much more rain falling in a very short period of time, and also because of higher river discharges. So we need to find solutions. We've had a major disaster in 1953. That was our last major flood that cost about 2,000 people their lives. And that was actually a turning point in our thinking about flood control. We started building these large infrastructural works, delta works we call them, that the Netherlands is known for. Jan Pelen will actually show you to a number of projects that are contained in there. But gradually also our thinking about flood control developed. So nowadays we're not so much thinking about large infrastructural works only, but we're also thinking about other things, because you cannot create dams, build dams, and raise your dikes forever. So we have come to the conclusion that we need to find other solutions, which basically are found in the principle of living with water, creating space for water in the built-up environment. That all in all proves to be a very successful policy. Since 1953, we do not have a single person dying because of a flood in the Netherlands. So that's nearly 70 years now. And that is quite an achievement if you consider all the situations that we were confronted with in the past. So it's not a coincidence, I would say, that Mumbai, Maharashtra, and the Netherlands are teaming up in water management and flood resilience. You will hear everything about the Dutch approaches in the coming 1.5 hours. But not, of course, after we've heard from Mr. Velrasu what the situation is in Mumbai, what the problems are that you have to cope with, and also the projects that you have in store and that you're working on. I think this webinar is, although it is a lot of Dutch presentations today, but of course, it's supposed to be a two-way street. So let's learn from each other. Don't shy back to ask questions. And I'm looking forward to a fruitful summer. And of course, let's see where we can find opportunities for future cooperation. So I look forward to the discussions, and I hand it back to you, Kailash. Thank you.
Thank you, Bart, for laying the groundwork for the discussion today. I would now like to invite Mr. Velrasu to deliver the keynote address for the session today. Mr. Velrasu is the Additional Municipal Commissioner Projects at the Municipal Corporation of Greater Mumbai, and as such, he drives the water, wastewater, and the flood management initiatives for the city of Mumbai. Mr. Velrasu, over to you, sir. Sir, you need to unmute yourself.
Thank you, Mr. Kailash. I thank Mr. Bart de Jong, Consul General, Netherlands, for having arranged this session. I thank him for this reason because the Dutch, they are very well known for handling these flooding issues, and their capacities in this field is immensely well known to the world. So we have always been impressed by their engineering skills, which they have demonstrated over a period, maybe covering over many centuries. Like the Consul General just now shown, had they not put those systems in place, most of the Netherlands would be underwater now. I am also impressed how seriously they take this work. For example, in Mumbai, when we design the structures, we design it for once in a 100-year event. So that is the kind of designs we do. But I understand when they do these type of works, maybe the delta works or whatever structures they build, I understand they do it. If it is a sea-based structures, then they do it for a once in a 10,000-year event. And slightly for locations placed in slightly in the upper reaches, they design the structures would stand at least for a once in a 4,000-year event. These are all extreme engineering, and they say only 3 things can control the sea. One is the moon, another is the speed of the wind, and the third is the Dutch, because they put all the structures in the sea. That is what they joke. So, but there is a truth to it. Like he pointed out, most of the land would be below sea level. I was told more than 55% of the land is below the Amsterdam sea level, and 60% of the population, they live there. And incidentally, 65% of the GDP comes out of that area. So it is a south and west portions which contribute more to the GDP, even though they are constantly exposed to the risk of the seawater. I see a lot of parallels between Mumbai and Netherlands, in the sense the problems would be the scale, but the scale is not. We don't have problem from the surging sea storms. We don't have sea intrusion into the city. but there are other issues we face. Those issues are similar to Netherlands. So I will share a small presentation. I will rush through it so that, because from Mumbai side, I am the only person who is going to speak. So it is better to put the background in perspective. So Mumbai is about 400 square kilometers and we have about 20 million population. So the density wise, it is as good as Netherlands. And we get a lot of our flood from the rains. The rains happen between June and October. So we get about 2400 millimeter of rainfall. Sometimes it goes up to 4000 millimeter of rainfall. So incidentally, the Mumbai is also reclaimed land because most of the places are filled up. Originally, there were 6 islands. So we are. So the idea was we filled the land and we formed a huge land mass. So that is where the similarity is there with the Dutch. And if you see our most of the water to drain this into the sea, these are all gravity based. We till recently, we have not put any pumping stations. So the Mumbai flooding problem, basically they are because of 4 rivers and the 4 rivers, when they drain water into the sea, supposing there is a high tide, then the water doesn't drain and that water floods the city. So we have 4 rivers like you have Rhine or Meuse and other rivers. So we have these 4 rivers. We have the Hisar, Poisar, Oshivar and Miti. So these rivers drain water into the sea. If there is a low tide, there are no issues. But if the tide is high, then the water doesn't discharge into the sea, creating flooding in the city. So this is a problem. And our systems, they have been designed only for 25 mm of rainfall in an hour. Now, under the global climate change, we see more than 200 millimeter of rainfall in 1 hour. So basically, our systems are under-designed and the kind of extreme events which we are witnessing now. For example, last year, we witnessed more than 200 mm rainfall in a day, more than 3 days. So these are the extreme events happening for the global climate change. Our systems are not designed to take on those type of extreme events. So the Mumbai has large number of channels which merge into the rivers and the rivers get into the sea. We have about 186 outfalls, the drainage points, out of which excepting 6, all other outfalls are below the sea level. Meaning when the sea is full and when there is a high tide situation, all these outfalls will not let the water go into the sea. So the city gets flooded. So we had a plan with us in 1989. So it is called Brimstone report. This is the base map on which we build our systems. We assumed the runoff coefficient as 0.5. Whereas in practice, it is close to 1. So this was going on for some time. Then the 2005, we faced a major flood. That is when the extreme rainfalls coincide with the high tides. So that day, the whole Mumbai got under water. Many people died. So you could see everything came to a standstill. So then what happened? The government, as usual, we again appointed a committee. Again, we studied. Again, the solutions were very normal. We had to widen the rivers. We had to deepen the rivers. We had to remove the people occupying those banks. All these solutions were given. And these formed the base map on which we are working our solutions. So this is how the methodology and all the details are there. But what we are seeing in the last 4 or 5 years, the extreme events are increasing in numbers. So the 5 years back, we didn't see much of these extreme events. So last year we got 4,000 millimeter of rainfall, which is almost twice the usual rainfall in Mumbai city. And 3 days we had more than 200 mm of rainfall. So all these events only strengthen the belief that in future, the risk because of the climate change as well as the rising sea level is there for us to face. So what we do, we have 6 huge pumping stations. When the sea water level is high, we put the floodgates, but the whatever water is getting collected from the rainfall, we pump them out into the sea. So we have 6 places. It is already in working stage. 2 places we are yet to construct. So to say these are like our delta structures. For our scale, these are our delta structures, even though they may be small. So these are the pumping stations. And many outfalls, we put this flooding gates type of arrangements and pump out the water into the river and into the sea. These type of arrangements we do. And you see, every year we remove almost 500,000 metric tons of silt from the rivers and other big channels to have a good flow into the sea. This we regularly do. Then, in spite of all this work, we have about 400 points. They are lower level than that of the sea level. We get water stagnant here. So we have to put these pumps and discharge them into the nearby channels and the nearby rivers. That also we do. So in spite of that, we have about 400 flooding spots, small flooding spots in the different parts of the city. Every monsoon it happens. So we already tackled about 170 places using engineering solutions. And the remaining places, we are in different stages of tackling. Now this is based on the Tokyo the tunnel model. Here, these are some chronic spots where we are building huge underground floodwater holding tanks. This for the first time we are doing this year. We have taken this work in 2 places on a pilot basis. We want to execute in 2 locations and learn from this. So one is the Hindu Mata area. So we will be pumping out the water to a holding pond. During low tide, we will be emptying them into the sea. So this is the other side of the same place. The work is in progress. This is another place called Gandhi Market. So this is for the last 20 years, this place is perennially flood logging area. So this year we have put a huge sump here. We will be putting huge pumps and we will be pumping out the water to the nearby channel. This work we have undertaken. Now some issues, they would be different from what is in Netherlands, in Mumbai. I will close with these issues. Here, the total funding of all these works comes from the government. There is no tax collected from people for this work. There are no local water boards. There are no local structures. Unlike Netherlands, where you have lots of water boards and you can, by act, you can collect tax from the people for the upkeep of dike and other structures. We don't have any system currently. But the flooding is a very politically sensitive issue. Even though it is sensitive, it is human nature. People don't want to vacate the banks of the river. Like you have the Room for River project where you shifted people out, but that might not be so easy here because the occupation is so dense in the informal structures we call slums. They don't want to vacate those places. So the widening and deepening of rivers, it is very difficult. And unlike Netherlands, here the floods are of very short duration. Even the water, the huge rainfall, even the flood situation is there. It is there only for 2 days, 3 days. Again, the normalcy comes back. So we are not pushed to the wall to put the anti-flooding structures in a massive way. So the short duration floods are in a way limitations. Then currently we don't have a policy of storing this rainwater, recycling it, reusing it. For example, I have shown the 6 huge pumping stations, stormwater pumping stations. We get a lot of good water from that. We pump into the sea. But for drinking water, we are constructing another 2 dams upstreams. So if we have a holistic policy, instead of construction of new dams, we could have used this water after storing and recycling. We could have very well reused the water. We could have easily recycled it. So that policy is currently absent. The climate risk, even though people say it is the second most risky city in the world, the water levels could rise up to 1.5 meters. Still, that message is well known to the people, but the immediacy to act upon that is still lacking. So these are the issues where I think we need to work more with these points for pondering. I once again thank and I am looking forward to know from your experience. Thank you.
Thank you, Mr. Velrasu, for putting the perspectives and issues, challenges faced by Mumbai. So a few questions that immediately come to our mind, sir, is that, as you said, the number of, incidents have been increasing in the last 5 years. Other than the Brimstone project, are there any other initiatives or projects that MCGM is thinking of, to control the flood management situation?
Yes, the Brimstone word also, the specification, the technical specifications, they say runoff coefficient is 1.5. But apart from the Brimstone word, we are also working for other concepts, other ideas. For example, we have appointed an international consultancy to adopt the sponge city concept, because we want to collect the water and store where it falls, because that is one way of preventing the flood. The flood holding tank concept we have adopted from Tokyo and Shanghai, but the scale is small. After we do this, the political leadership is of the opinion we might do it in a large scale in many locations. We will scale it up after observing this monsoon. So the sponge city concept, these flood holding tanks, they were not a part of the Brimstone. So these are the new concepts emerging. And after this international consultant studies and give presentations, we will adopt the new concepts also. So that is, we are open to all the new concepts also. Yeah.
So, one final question is that globally we have seen that most of the utilities or cities are slowly using satellite technology or GIS-based mapping, in their fights to design their networks to tackle flood management. Has MCGM also done any kind of work in the area of GIS mapping or satellite imagery to, design their networks better?
That discussion was done. It has been going on for the last 10 years. I think one of my presentation I have shown, we have created the 2D model, 3D models, and we have done the LIDAR survey. In fact, currently we are in discussion with our meteorology department, because we will be putting these 3 Dopplers, and we want to do get the real-time data about the rainfall possibilities, different scenarios. And we want to put the sensors in all these our drainage, underground channels and rivers. So we want to have an integrated flood alert system. But these things are in a very initial stage. I won't say they have matured and practically being used in Mumbai now. But these concepts are now currently being explored. So these concepts will be put in place maybe in matter of another 5 to 6 years. They are under discussion stage now. Yeah.
Thank you, Mr. Velrasu, for your insights. I'm requesting all the attendees that in case they have any questions, they could put their questions in the Q&A box, and we can take up these questions during the Q&A session. I would now like to move on to our next presenter for this workshop. I would now like to invite Mr. Ian Peelen. He's from the Ministry of Water and Infrastructure for the Kingdom of Netherlands. He's going to talk about living with waters, how the country of Netherlands prevents flood disasters. Over to you, Ian.
Okay, if I'm audible for everybody, I will start sharing my screen. Here we go. Yeah, so I'll give you a short presentation on the Dutch approach to floodwater management and land subsidence. and also try to reflect how this leads to lessons learned from other countries. My background is I've been working in the US for quite a while, until December last year, in basically helping American agencies and local governments create climate adaptation plans. And I will also, use some of those lessons in the presentation. A short introduction to the Netherlands. Actually, Ms. Velsrau, you actually, and Bart, you already gave a good introduction. The Netherlands is a small, densely populated country. It's 17 million people, with, just like Mumbai, a big port, big airfield. It's really an economic cluster, but it's also under the threat of water. And actually, in the Netherlands, it's always have been. The Netherlands literally means the Low Countries, and that it shows we are not based on islands, but we are situated in a delta. That's the whole reason for our dense population. The delta always attracts a lot of people and a lot of commerce. And just like Bart already referred, the Netherlands has a history of flood management. A large part, like 30% of our country, is below sea level, and 60% of our country is actually prone to flooding if we wouldn't put on flood defenses. And as you'll probably guessed, that's exactly the part where we concentrated all our most of our activities. So 60% of our GDP is earned here, 60% of our people live in the area that are prone to flooding. And historically, the Netherlands has always been a country that basically had to learn to manage floods if it wanted to exist. And if you can see on the map on the right, that's actually an oversight of all our land reclamation projects. We didn't fill up between the islands. We basically drained lakes, and as you can see, the spots, they start in the 40s. We actually started in the 14th century with land reclamation projects, and as we got our hands on new technologies, the scale of those reclamations just grew and grew. This history of flood management also helped us to create the governance structures that are useful to protect us against these systems. So we have, like you said, they already mentioned, we have these water boards that are totally dedicated to manage water. They also can levy dedicated taxes for these tasks. So that basically really primes us the fact that we basically have to, like we said, we either have to pump or swim. Really helped us develop a government structure and policies that are really helping us against flood and climate change. As already mentioned, 1953 was our last big flood that actually led to huge economic damage, and about 800 people died in that flood in 1953. And that led us, like I said, I've worked in the US for quite a while, and I also, this project led to the Delta program, and I always liked to refer to that as our Apollo project. It's roughly the same time when the Americans were focusing on getting a man on the moon, we were focusing on keeping our country safe against water. Basically, what we did was create a fortress against the sea. So we created all these heavy engineering infrastructures just to keep the water out. As you can see, these are very famous pictures. Is the Oosterscheldekering. And this is actually, the next one is the Maaslandkering, which is a movable barrier that protects the port of Rotterdam, one of the biggest ports, actually the biggest port of the world outside of China. So this was actually a multi-decade, multi-billion project. So basically we started, planning this project in the 1950s after the big flood. And we actually finished this particular structure in early 1990s. And well, even in Mumbai, everybody knows the Dutch Delta Works, and the American Association of Engineers called it actually one of the modern wonders of the world. So when we created this and we finished this, you can expect that we were pretty pleased with ourselves. So our country is safe again. Unfortunately, we learned very quickly that we do not control the weather. Because we just finished this one, and then nature actually sent us a sweet reminder that she could also flood us from the rivers. This is not, this server is not our idea of sustainable transportation. This is just somebody surfing one of our important highways in the 90s. We had 2 years in a row that we had massive floods from our rivers. Nobody died, but still it was quite massive. Also, the weather patterns are changing. We have more intense rainfall. We have actually, especially compared to Mumbai, we have a very moderate climate, but it's changing, and we get these very intense rainfalls now. Same river that actually led to the server using the highway is this a couple of years ago. We actually have droughts now. So, and that's for us, the country that has a history of keeping the water out. We now have to start thinking about keeping the water in because we need the water for drinking water, for cooling water, for energy, but also for our many maritime activities. We use the rivers for transportation. So how are we going to manage all these new challenges that we get from climate change? And more importantly, how do we deal with the uncertainty? Because we know that the sea level is going to rise. We know that our country is subsiding. We know that we're getting more extreme weather, but we don't know how bad it will be in 10 years, in 20 years, let alone in 100 years. So basically what we created was what we call the Delta program, which is not a policy, but it's a framework. It's a framework that helps us deal with the uncertainty of climate change. It gave us new political, administrative, legal, and financial measures. So basically, with these new changing conditions, who's responsible for what? Is there a dedicated fund that we can use for climate adaptation projects? Putting in legislative requirements for governments to update their planning to keep in pace with the new conditions. So what we really did is incorporate prime our system and incorporate uncertainty into the planning process and using scenarios. And this whole idea, like I said, there's a very, as you can see, very ambitious time scale, year 2100. Most of us will be retired then, or not be around anymore. But how do you make this long-term plan and still keep, it in pace with the short-term action? And that's actually the challenge that we're facing. But we do want to make it integrated. And we sometimes agree that we really have to make a radical change in the way we think about things. It has to be sustainable. We have to stay flexible, but also there has to be solidarity. And solidarity means that, not one part of the country is paying for everything, but it also means generational solidarity. So future generations should not be put up with additional costs or challenges because we don't do anything. So a couple of examples of projects that really showcase the new way of thinking. This is actually a coastal project protecting the popular beach town of Scheveningen. We know that through sea level rise, we had to build a new kind of levee in this area. But the problem, it would be a very high seawall. Putting it in place would basically destroy the appeal of this city and its beach. So what do you want? Do you want tourism and economic development, or do you want to have a safe city? And basically what they did is actually what you see in the picture. They did both. Instead of building a high seawall, they instead of thinking about the problem, they thought in solutions and ambitions. So what they did, they extended the beach, which actually captures wave energy, which actually will allow them to have a lower seawall. And then they found additional budgets to really design the seawall, not as a seawall, but as a nice boulevard. And that's what you're looking at. You're looking at a really fancy seawall. And the thing about it is that this project now generates money instead of, it costs a lot of money to protect the city against a 1 in 500 year event. It now generates money all the time instead of, just preventing damage this one time every so many years. Another project is with the same attitude is this. It's called one of the most famous projects for a room for the river projects. This is actually a bypass in the River Rhine that we had developed to make sure that with high water discharge in the River Rhine, the city on the left, the city of Nijmegen, doesn't flood. So we put in a bypass. The additional benefit of this bypass, it's actually that it generates opportunity for recreation on the other and new urban development on the other side of the river. And what you now see is that it is not just an engineering project. We actually created a whole new part of the city, a part of the city that people use. Again, this is not about preventing this 1 in so many years event. It's also creating added value for all the other years that you don't have to use it. And that's the same we do with big scale. Those are big scale projects. We also try to do it on small scale. This is in Rotterdam, one of our cities that's really really leading on resilience. They are actually redeveloping their public space to make it flood proof. So this is actually a square, and usually it has a small waterway under the bridge, but it's also now has a double function. Instead of intense rainfall, all the water in the area floods to this particular place, and they designed it that it's okay to flood, so there's no damage done. So that's the general idea and some practical projects. We already talked about these, like I said, about these events in the previous presentations. We already talked about the concept of floodplains, these 1 in 100 year events, 1 in 10,000 year events. The way we talk about risk is actually one of the big problems in handling this. And I actually got this number of slides from somebody from the University of Georgia. What is a 100-year floodplain? That's actually quite hard to communicate to people, not just to the general audience, but also to politicians and other professionals. What is a 100-year floodplain? Does that mean that the entire floodplain floods 1 in 100 years? No, that's not the truth. Actually, there's the 100-year floodplain has different zones, and there are different flood risks associated with that. As you can see in this picture, but still, what does this mean? Does it mean that if I build my house on the spot where it is that there's a 1% chance every year that my house will flood? Does it mean that my house will flood, 1 in 100, once every 100 years? I actually spoke to a mayor in the US. He said, well, we have these 1 in 100 year events. The problem is that we have them twice a year. And last week we had it twice in 1 week. So, he was really struggling with how do I communicate that to my population. And actually this percent, we really have to rethink the way we talk about this risk level. And actually I like this percent, the 1 in 100 year chance of having your house flooded actually means, we really try to communicate it in a way people understand. In the US, the average mortgage is 30 years. So if you have a mortgage on your house, what's the chance of your house being severely damaged during the time that you have a mortgage on your house? Well, and then it comes that even, if your house is on the safest spot in the floodplain, there's a 26% chance of your house being severely damaged during the time that you have a mortgage on that house. If I tell people like there's a 1 in 100-year chance your house will be flooded, people will go, that's fine, I will buy this house. But if I tell them there's a 26% chance that during the time that you have a mortgage on the house, your house will be damaged, that's a whole different risk perception that people have. And this is actually one of the big challenges we're now facing, and not just with my work in the US, but also with work for example, projects with the World Bank or in the Netherlands. And we actually, in the Netherlands, we are now changing the way we talk about risk. We're letting go of the 1 in 100-year floodplains. We're really focusing on the things that we want to achieve, like Bart already mentioned, no people dying, or trying to make sure that damage is not, the damages are doable. And we actually are trying to, also share those lessons with Mumbai, but also with other countries. One of the, the longest running projects is Louisiana. Louisiana is a state in the Gulf of Mexico. It's where the Mississippi ends and comes into the Gulf of Mexico. And they have very similar problems. They have low-lying lands, a lot of subsidence, but actually also the sea is, through sea level rise, is eating away the land. They're actually losing like 4 soccer fields. I don't know the conversion rate of a soccer field to a cricket field, but they're eating away 4 football fields. They're losing 4 football fields each day. They actually learn from, we've been in exchange with them for a couple of years now, and they actually really adapted our way of thinking, but they adapted it in a style that really fits Louisiana. So they created their entire own climate adaptation project. And like you said, they have 124 projects. Their flood damage is severely reduced, and they're actually reclaiming land right now. So this comes to show that, you can learn from the Netherlands, but you really have to make, don't copy us. You really have to make it your own. We can help you, inspire you, but you really have to make a system that fits, in this case, Mumbai. And then the Dutch perspective, my summary. Climate change is not something of tomorrow. It's already here now in the shape of events, but also the fact, like you saw in your presentation, that you're already, touching your annual average in August. You still have a couple of months of monsoon left. And not just events, but you also have to think about there's a new normal. There's not just these once in a lifetime or once in a 50-year event. It's the new normal. And we as communities, we all need to redefine our relationship with water through that. And that can be very different. The problem is in Mumbai, that relationship will be completely different than somebody in New Delhi. So there's a really, the approach to this is really, really regional. And the problem is that our current government models, our current business models are usually not really they don't really help us. They have not been designed to tackle these kind of issues. They're often sluggish to change, or actually they resist change because of established interests, or just for politicians it's really often very scary to communicate these uncertainties, or have the for example, the replacement of people. Sometimes it's really necessary, but nobody really likes that message. This is an ongoing learning process. If you see my presentation, the things we built in the 50s were, true engineering. We've learned from that. It's not just engineering anymore. It's also urban planning. It's also, a financial issue, more and more social, especially in a city as Mumbai. You're so much more densely populated than the Netherlands. this is not, you can't engineer your way out of this. This really has to be a very integrated approach. If you're looking at it from a financial perspective, from a social perspective, and engineering is just one of the issues. But that really requires a lot from our professional communities to start talking with each other and understanding each other, what they mean and what they need. And then my two hobby horses, if I would like to say them, we still don't know how to talk about risk. We really have to learn to communicate that better. And we have to learn how to make lemonade out of lemons. So if you can't, it's just not financially feasible anymore or socially feasible anymore to just build engineered solutions like a pump or a levee. You really have to do the entire package. And with doing the entire package, you actually also find new business models to pay for this infrastructure. And that's my presentation for today.
Thanks, Ian, for sharing the Netherlands perspective and how Netherlands is tackling the flood management issue. So we have had now 2 sessions, one from Mumbai on how they are tackling or facing the challenges around flood management, and second from Ian on how Netherlands is doing it. Now we move on to the technology solutions on how these are possible, and our next speakers are primarily going to provide us with technology solutions on how we can prepare ourselves better to face this challenge. So for our next presentation, I would now like to invite Mr. Mark Lane Brettler. He's the project manager for research and specialist at Delta Flume, and he's going to talk about the Delta Flume, a versatile tool to support innovation. So over to you, Mark.
Yes, thank you for this introduction. I will now share my screen. Okay. I assume that you're now seeing it. And I will
visible.
Go to full screen. Yes. Okay. So my name is Mark Lane Brettler. I'm a project leader at the Delta Flume of Deltaris in Delft. And I have a short presentation about this Delta Flume, which is a powerful tool to support innovations for flood management. The Flume is capable of generating the largest waves in the world. We can generate a wave height, a significant wave height of 2 meters, but that is a sort of average value. Our largest wave is 4.7 meters high, which is 2 stories, is really gigantic if that's running through the Flume and hitting on a structure. The length of the Flume is 300 meters. The depth is 9.5 meters. And you see some pictures here. It's really huge. Usually you do small scale modeling if you want to solve a problem with experimental research, but it's not always possible to use small scale modeling. Sometimes you have to go large scale on the scale of the Delta Flume. For example, for coastal structures or river embankments of large rivers, you can cope. You have to cope with wave impacts. Wave impacts are also influenced by scale effects because of the air bubbles that are entrained in the water, but also with other topics like researching vegetation, the influence of vegetation on coastal structures or your rivers. That is aligned with the building with nature. And durability aspects can also be researched here, and testing equipment and construction methods. But also in the energy transition, we nowadays do a lot in offshore wind turbines, and wave attack on offshore wind turbines, especially substructure, is influenced by scale effects. So there you go on large scale. There's also for bottom protections around these structures, but also at soil mechanics. By soil mechanics, if you have waves that interact with the soil, then you get deformations in the soil or erosion, and these topics are typically also influenced by the scale. So you need to investigate this on large scale. Well, I have a number of examples to show what we do in our Delta Flume. And this is example number one. It's an innovative block revetment called Hill Block. And we developed that together with a client. And because of this special shape of this concrete block, we only need half the amount of concrete to withstand a certain wave conditions. This is typically used to pave the embankments of large lakes or along the coast to withstand the wave attack on the embankment or the dike. That development was very successful for this private company, and by doing those tests in the Delta Flume, we can show that it is really working well. And it also attracts a lot of media attention. So we also invited the potential clients for this private company, and that gave a huge boost in the market introduction for this system. And that works very well in the Delta Flume. Another example is what we did for a client in Australia, and that is he has invented a fiber reinforced polymer sheet pile wall. Sheet pile walls are normally constructed with steel, which is very stiff, but this fiber reinforced polymer sheet pile wall is very flexible, and that has important advantages. And it is also durable because it doesn't rust. Well, with two of these sheet pile walls with sand in between, you have a water defense, and we have tested that in the Delta Flume. We started with normal waves, but they reflect on the structure, and there's not much forces on the structure, so that is quite easy for the structure. But then we took it to the next level. We created breaking waves that really collapse on the structure. And you can see here in the pictures that gave enormous force on the structure. The 300-ton structure was pushed back 14 centimeters, which shows that these forces are really tremendous. But on the other hand, it also shows the flexibility of the structure. It didn't collapse. This structure just withstood these enormous forces magnificently. Another example is that we investigate erosion problems in the Delta Flume. On the left, we have a picture of clay and grass, which is typically used in many embankments along the big rivers, and but also on the coast we have dikes with clay and grass. And here we are investigating the erosion of that material. It's typically something that you cannot do on small scale because clay cannot be scaled and the grass also is not. In the middle, we have a sand dune, also an erosion process. And on the right, you see our tools to show the erosion and analyze the erosion hole that occurs during the tests. Example number 4 is about the offshore wind turbines. You see here a pole on which a normal wind turbine is installed, and we are testing here an innovative bottom protection structure. Those structures, they cause an enormous amount of erosion around the basement, and with a proper bottom protection you can prevent that. But we are building now so many of those in the North Sea, but around the world, that it is important to have an efficient way of protecting the bottom around the offshore wind turbine. That is what we investigated here. My last example is here a willow trees. We have been testing a forest of willow trees in front of a water defense. And the idea is here that the waves have to propagate through the forest, then the wave height is reduced, so the water defense is attacked by much smaller waves than without the forest. And this is a typical example of building with nature. We use a nice forest that can be used for recreational purposes throughout the year, but on those very rare events with high water, it serves as a breakwater for our water defense. And that can be used with willows, which is a typical tree in the Netherlands. But translating that to the tropical areas, you can use here the mangrove forests, which are quite common, of course, in the tropical areas, but are endangered because of all kind of activities of people. These forests are endangered, and that is really so we have this investigated here. So looking back on these examples, you can see that the Delta Flume is a versatile tool to support innovation. So well, if there are questions, then I'm happy to answer them, but this finishes my presentation. Thank you.
Thanks, Mark, for sharing this, innovative solutions. In case the audience has any questions, I request them to put it in the. It has come from Mr. I think Ian Peelan. The question is from one of the attendees saying, what is the method followed by you for early warning of any incident?
Sorry, I didn't understand the question.
The question, I think, is more for Ian. Warning.
Yeah, your sound is very difficult now. You are.
I cannot hear you too.
No, yeah, you're very difficult to hear.
Yes. Apologies for the comment.
So I don't know if it is clearer now. The question is, what is the method followed for an early warning system in Netherlands?
Yes, well, we have, of course, a whole system of early warning that is basically something which the government organizes. We have a location in Lelystad where the weather forecasts are looked into, and when there is a huge storm coming up or large river discharges coming up, then gradually we are scaling up our response to that. And in the ultimate upscaling, we have all people watching our dikes and also calculating possible scenarios of events so that we can decide on whether we have to evacuate somewhere people or not. So that is a whole system which is also tested now and then. We have every 1 or 2 years we have a big training campaign where a lot of people involved in this whole system are training for the event of some high water or that sort of things. Yeah.
Thanks, Mark, for giving us Also, a question that has come from Yogesh is, how much layers of hill blocks are necessary, and what is criteria for its fixing?
There is only one layer necessary. In the picture, you saw the layer of blocks, and that is the only layer that is put here on a gravel subsoil. So there's a filter layer of gravel. And these small blocks, which are typically about 40 centimeters, 0.4 meters thick, is already sufficient to withstand wave heights of about 3 meters. So this is a very effective system. You don't need much concrete to withstand the waves.
Thanks, Mark. I hope it answers the question from put up by one of the attendees. So moving on to our next presenter, I would now like to invite Professor Dr. S.N. Bas Onkman. He's the head for hydraulic engineering at the Technical University of Delft, and he's going to talk about adaptation to sea level rise, Dutch experiences, and global challenges. Over to you, Professor Bas.
Thank you very much. Good afternoon. Also, given the time schedule, in this presentation, I want to cover 3 or 4 topics quite briefly. Of course, more details can be given at a later stage. The new risk-based safety standards for flooding in the Netherlands, some key examples of projects for adaptation, and a bit of the international involvement. I think the context and scene on flood management in the Netherlands has been already illustrated very well by Mr. Jan Pelen. We have different types of floods: the rainfall, pluvial flooding, typical local effects, standards 1 in 10, 1 in 100, local canals, dikes that can fill, and what we are most concerned about, and what I will also cover today, is the failure of primary flood defenses on the large rivers, the coast, and the large lakes. As already mentioned, most of the Netherlands is prone to flooding, the light yellow area. Majority of the people live in these areas, and that's why over the centuries the Dutch have developed this comprehensive flood management system in the coastal zone, consisting of the dikes and dams of our delta works, some storm surge barriers, like here's the barrier near Rotterdam, the Maasland barrier, which is in normal conditions open to allow shipping, and as in the picture, during a storm surge it can be closed. Large part of this part of the coast is covered by sand dunes, which are maintained by dredging. And in the northern part, you see this line of the 30-kilometer long Afsluitdijk, closure dam, and dikes in the north. We also have along the rivers, the combination of basically the Room for River program, increasing the discharge capacity of the rivers in combination with dike reinforcements along the rivers. In total, it's a system of about 3,800 kilometers of primary flood defenses, as we call them. In his introduction, Mr. Velras, who already made very interesting observations about the safety standards, and indeed these differ around the world. In the Netherlands, until a few years ago, the safety standards were based on design water levels with a certain probability of exceedance. For the most densely populated areas, 1 in 10,000. For the riverine areas, 1 in 1,250. But over the last decade, the government has decided to change and update those standards based on a nationwide risk assessment, because these standards have been developed in the 1960s, 1970s. And since then, the values that are protected have grown a lot, and also the knowledge about the risks, both the consequences and the levee failure probabilities, have also increased. So what has happened is that over the last decade, and I can share details later, a nationwide risk assessment has been carried out, indicating both for loss of life and economic damages where the greatest risks are found in the country. And you get maps like these that show the individual risk, individual probability of being killed due to flooding, which are in this map particularly high in the riverine areas because they are deep and because the failure probabilities of those riverine floodings were expected to be high. And what has been done based on all these information, also a cost-benefit analysis has been carried out of the costs of higher protection and the economic risk reduction. A whole new series of safety standards has been proposed with different values, even going up to greater values of protection, 1 in 30,000. Also more differentiations. So if there's lower consequences, a lower value can be picked. And here also, and it's maybe more technical, the concept of probabilistic design of failure probabilities has been embraced. So this number refers to the failure probability that a section of embankment or dike should have. So this is the new, let's say, standard that dike designers and authorities work with in assessing and designing reinforcements. As an intermezzo, it's always nice to compare these numbers around the world. Again, the Dutch numbers have changed from here in the middle of the table, a design water level approach to even higher safety standards corresponding to the probability of failure. This is really for catastrophic flooding, billions of damage, large loss of life expected. Well, you see around the world that in areas in Shanghai where they expect from coastal flooding also billions of damages, they are also moving to higher safety standards. And in Singapore, where they are doing a land reclamation and where they are quite risk averse, they also are moving to higher safety standards. But in many parts of the world, indeed, the 1 in 100 is the standard. And one interesting aspect could be to carry out such a risk or cost benefit analysis to see what could be adequate levels of protection included in the standards. This has been already largely been explained by Mr. Jan Pele, but we have a large amount of defenses. Every 6 to 12 years, they are inspected or assessed if they're still safe enough. And I think the good thing is that in the Netherlands, we have this kind of national program with over €1 billion per year to continuously invest in the reinforcements, not in a single project 1 year, but over time, if you continue doing that for decades, you can upgrade the system. Well, what are the kind of trends in the kind of projects? On the coastal side, we see that there's more and more attention for, where it's possible, for nature-based solutions. And one of the more recent examples was the, let's say this is one of the coastal dikes, which used to be a hard defense and has been changed now into a dune landscape with a lot of dredging, of course, on the coast, but it's still the same area. Also multifunctional solutions, or we call it combined hybrid solutions, where a hard dike, this is in Noordwijk, is covered by means of a dune, and the previous presenter showed these the delta flume, and that's typically needed to test these type of designs, how they function. Also more and more attention for, I would call, landscape implementation, both in the urban and rural environment, which also leads to multifunctional projects where in Katwijk, the parking garage is connected to the sea defense and implemented in the, let's say, town. And this is an example of also a hybrid solution where an existing dam in a lake environment is particularly reinforced over a large area by means of foreshore nourishment. And I know that in Mumbai there are plans or there's work on the coastal highway, and there may be combinations also with nature-based features or multifunctional features could also be of interest. Then there's the question of how to deal and think about sea level rise, and you can talk about that for a long time. And a recap of various previous, let's say, assessments we did with groups of experts is as follows. On the horizontal axis, you see the time. On the vertical axis, the sea level rise in meters. In case of the low emission scenario, it would stay up to 1 meter. It's probably less expected. If it would, in case of high emissions, it would go to anywhere between 2.5 and 5 meters. In the current system of defenses, a kind of margin in the coast is generally included of up to 0.5 or 1 meter of sea level rise as one of the margins in the design. So in general, you can say current system can adapt or can cope with about 1 meter sea level rise. Above that, the first bottlenecks will emerge, particularly at those movable barriers and gates, like these Maasland barrier, which have to close more frequently, for which the reliability will become a problem, the impact on shipping, or a similar story for the Eastern Scheldt, but then the impact on nature. So there's the first, let's say, issues, and the plans have to be made. Okay, what are the solutions that can be used then? Even a closed dam with sluices for shipping. Then we have looked, okay, for several meters, from an engineering and a financial point of view, we expect that it's possible to adapt defenses, both the rivers and the coast, to upscale nourishment, also considering the sand supply, but it will come at a high cost and a high societal impact also because of the construction works and the footprint of those defenses. So it's definitely a large project. And then there are these, let's say, futuristic visions that in case of large sea level rise, maybe we need to migrate to the east. The Netherlands will become a kingdom of even more islands, or move forward, build large dams to protect the entire North Sea, including parts of the UK, France, Belgium, Denmark, Netherlands, and so on. And we expect that those will become, let's say, more relevant. The time that the existing technical solutions will become more problematic will be above these 5 meter sea level rise. But we have to definitely study those, and as in Mumbai, particularly the combination of discharge, increasing sea level will become a major issue already, starting at 0.5 to 1 meter sea level rise. Internationally, we see that, of course, there's all these mega cities even growing further in delta areas, and that is also why, also to sharpen our own knowledge, to work together with international partners on these issues. We've just completed a 4-year research project funded by the Dutch, and Chinese and UK science councils on building a whole risk modeling and adaptation framework, coupling climate models, embankment failure models, flooding models, and adaptation options for the city of Shanghai. Well, I say city, but it's actually the size of our country in terms of population. And one area where we are particularly active is Texas, the area around Houston, which is also prone to flooding from hurricanes and heavy rainfall, which was affected relatively recently by enormous amounts of rainfall, up to over 1,000 millimeters in one event, mainly river flooding, but also in Hurricane Ike, it should say 2008 here. The coastal flooding. So they also have both problems, maybe even simultaneously. And over the last years, also with our students and knowledge partners there, we've worked on designing, let's say, the Texas version of the Dutch Delta Works. That's, of course, only one of the options for this region, covering sand dunes, plans for storm surge barriers to keep the port of Houston accessible. And that's, let's say, the result of such a partnership also with the academic groups there, but also, let's say, taken up by the government. A few closing remarks. As already stated, flood management is essential for the Netherlands. So it's a continuous task, continuous investment, but also continuous knowledge development. This risk-based approach we feel is really useful for, well, having discussions or updating safety standards, but also for prioritizing projects where you have the greatest risk or greatest contribution to risk reduction. That those would be the most interesting projects. In the Netherlands, a lot of work is ongoing on upgrading defenses, both in the coastal and riverine environment. Not all of them, but in many places we see that innovative solutions, either nature-based, where there's space or in urban areas are gaining ground because also the societal impact and let's say enhancing the quality of the landscape is so important. And finally, we feel that we share many challenges internationally, and that collaboration and joint research, joint development of ideas and solutions can all help us. So I hope that gives you a snapshot of the things we are working on, and I would be happy to take any questions or comments.
Thank you, Dr. Bas, for this presentation and sharing all the inputs. We have a question for you. The question is it viable to construct a wall along the coastal line to get?
Yeah, I see the question. Well, it is a good question. There are many, for the Netherlands, many versions of the wall. One idea is just to upgrade the current system, which you could, are already to a large degree consisting of dams. There are other ideas that say, okay, let's build maybe a soft wall with nourishment in front of the coast and use that land to increase the land area. And the third version of that is the North Sea wall, where you built it from UK to Norway to protect the whole North Sea. Viability, technically, I think, particularly, let's say, raising the existing defenses is possible for several meters of sea level rise, financially as well. But again, all these plans require more, let's say, engineering design, research, but also public discussion on what we want and what we want to implement at which moment. But there's much more to say about it, but I'm afraid I have to leave it here.
Okay. Thanks, Dr. Bas, for sharing your presentation. I think we have one more question. I'll just take it. The question is, what are the main variables considered to decide high safety standard in assessment?
The height of the safety standard is based on the risk profile. Basically, two types of risk have been considered. The risk to life. So if you have an area with very deep flooding, many people will get a high safety standard. And an economic cost-benefit analysis has been made. So the cost of heightening the defense versus the economic risk reduction has been considered. So the cost-benefit analysis. And that type of calculation we always like to make with partners also for other cities around the world to have a discussion on the safety standard. And as a third, but that's more an exception, if there's really a special land use, a nuclear reactor, for example, behind the coastal dike, then it could also be decided to raise it to a higher standard. But that's more a local exception.
Thank you, Dr. Bas, for sharing your information. Moving on to our next presenter, I would now like to invite Ms. Supriya Krishnan. She's a PhD researcher and fellow at the Technical University of Delft, and her presentation is on urban planning under climate change for Mumbai. Over to you, Supriya.
Thanks, Mr. Shirokar. I hope my slides are visible.
Yeah.
Yeah, thank you. Well, good evening, everyone. Thanks again to the good people at the Netherlands Consulate and to Professor Bas Jonkman for this opportunity. As per my introduction, I am a PhD researcher at the TU Delft, same university as Professor Jonkman. I'm part of a 4-year PhD research program that looks at urban planning under climate change for the city of Mumbai. I also happen to be originally from Mumbai. That's where I am right now. I studied architecture also in Mumbai at JJ before I moved abroad to the Netherlands for my further research. So in addition to the PhD funding itself, this research is also supported by a grant of the Government of India from the Coalition for Disaster Resilient Infrastructure. So we recently have a dedicated grant to focus our research on Mumbai. So I think this slide is very much in resonance with what Velrasu sir said in the beginning about Mumbai's risk exposure, where we have a lot of chronic stress that's yearly. In addition, we also have projected risks uh, with in relation to rising sea level rise, and the numbers are significantly high. In many ways, Mumbai is a prisoner of its geography, also in the way it's situated, the way land has been reclaimed, the way density is distributed. So, in order to tackle that, we do have a very comprehensive development plan that lasts from until 2036 now, I believe, which sets out very strong environmental sustainability goals, as well as a dedicated chapter on climate ambitions that the city needs to deal with. However, as we already saw in Sir's earlier presentation, the on-ground complexity for bringing in any form of structural changes uh, in the form of, let's say, bringing in a room for the river, a seawall, nature-based solutions in the city of Mumbai. The complexity that's already on ground in terms of the densities is significantly higher. There is extremely little room for adjustment spatially to bring in new things or to rejuvenate new things. The development planning cycle, although is 20 years long, is relatively shorter to really bring in these kind of long-term considerations of climate that's changing far more rapidly. And all investments that we are making in the city at this point, be it the metro, the coastal road, the developments around the metro, the changes in FSI, are going to last much beyond the cycle of the development plan. So, in such a situation, what the PhD research is trying to look at is what is the future of the city Mumbai will look like. In that, we look at three main aspects. Number one is how is climate change impacting Mumbai's urban growth over the next 20, 50, or 100 years? How can the city densify or re-densify? And how do we make sure that in the face of such rapid changes, uh, the high investment areas do not coincide with the high risk areas? So, in order to do that, what we are working on is a risk informed urban planning framework for Mumbai. So, if you see the timeline on my screen from 2019 until 2100, we have development plans that are being made for, let's say, this 20-year time frame. And what we are trying to do is develop a comprehensive framework that allows a development plan or a master plan that's made for 20 years to consider climate change or other engineering simulations for which the time span of information available is much larger. So a disclaimer here is we are not trying to make a master plan for 2100 for Mumbai, but we are trying to make a framework that can guide a more informed short-term master plan that can be informed by longer-term climate simulations, such that we can move from a very fixed development plan that does work, but we kind of move to a more adaptive form of development for Mumbai. In order to do this, there are two main steps that we are using in the method. Now, what you see is basically a land use simulation for the Netherlands using one of the growth models that we are working with. So in the case of Mumbai, what we have started doing, so this research already started in 2019 and will go on until 2023. So we have been interviewing a series of experts who work on planning, disaster management, climate, environmental related issues in Mumbai, also some from the MCGM. It's quite an unfortunate thing that our field work coincided exactly with the pandemic years. So meeting people in person has been that much harder, but we are trying to conduct as many online consultations as possible. And the second and the more technical aspect of this research is we will be trying to simulate urban growth scenarios for Mumbai under changing climate projections over the next 100 years. And by climate projections, we would like to include the projections for sea level rise, temperature changes, of flooding and inundation models as much as is available at this point. So what we plan to do is over the next 80 years, for every 5 or 10 years, we would like to use these set of models to generate something like a suitability map. So what are the most conducive areas for development? Where should development be avoided? So this is something that can augment the making of the development of future development plans for the city, just to get a sense or get better evidence of where development should or should not happen. This is a complex project, which is why collaborations with city officials and city researchers is really, really key. We have interviewed a lot of people, but lack of access to data is really a big roadblock in conducting this type of research, which involves quite a heavy simulation modeling environment. So we are looking for land use, hazard maps, and inundation models that are available for the city. We would like to interview more experts within the MCGM and MMRDA framework, especially those who work closely with disaster risk management and closely with planning decisions for the city. We are very open to project partnerships and joint case studies. And early in 2022, when we have our first results from the models, we would like to conduct a technical feedback workshop together with some officials from the city. So that's the collaboration that we are looking at right now. Yeah, so that's my presentation. Thank you.
Thanks, Supriya, for sharing, details about the project. And we have the MCGM team here, and I'm hoping that, the people responsible for this would, maybe share and collaborate the data that they already have, which might help you in during your project. So thank you very much for sharing the details. Moving on to our next presentation, we have two more technical presentations for the day. I would now like to invite Patrick Stoppelman from CIDCO. He's going to talk about urban water management using satellite data. So over to you, Patrick.
Thank you very much. Good evening, everyone. Live from Amsterdam, Patrick Stoppelman. I work for CIDCO. And here's my email. And what you see is here, the background is Yangon. And let me go to the, let me go to the next slide. And here you see New Orleans. It came already by, and we use INSAR. I will get back to that on the technology. And there's quite some interesting observations you can make. On the left, you see a red line, which is a levee, a dam to protect against the sea. And it's apparently suffering from subsidence, as you can see the red color, and you look at the color map on the right top. Then you see in the middle, you see something like a subsidence bowl, red and orange and yellow. And then from the middle to the right, you see a bluish area. And that has to do, it's part of a study that we did together with a research institute, Deltares, has to do with groundwater, that there is an uplift of groundwater. So already in this one image, this one study, you can see that there's a lot going on in an area in New Orleans. And bringing you to the next slide, this is Amsterdam. Here we did a precision analysis using high-res data, 50 million measurements. We use this to collaborate with the engineering department for all kinds of research into monuments, into infrastructure. But let's first go to who we are. CIDCO is the company I work for. We do INSAR, and we are something what is qualified as a space downstream company. We're 12 years in business, quite some time. We have offices all over the globe, as you can see on the little map. We have 35 staff, a very international team. We also enjoy people from India in our team, which is great. Basically, we consist of INSAR specialists. Many of them have a PhD, and a lot of consultants with a master's degree. We consider ourselves to have geodetic DNA and a geodetic approach. And the reason I underline this is there's quite a lot of companies that do INSAR with a big data or an IT focus. And we believe that the result is color dots and not a result. And finally, we have our roots going back into Technical University of Delft. So this also gives us a link into the scientific world where we qualify every time new developments into our chain. Oh, pardon, it's going very fast. Just as a last one, civil mining, these are sort of the fields we work in, all kinds of civil object structures, mining, energy, government, and then focusing on national government, municipalities, water boards, all kinds of other in between organizations, and then international industries, a summary of all the other activities. Let me go to the technology. So here you see a simulation of a Sentinel-1 satellite. It's a constellation. In fact, it's a polar satellite, and it's covering the whole world. Because it's a constellation, there's a number of satellites that does this. And therefore, you get ascending and descending observations of the Earth, one time from north to south and the other one from south to north. We make use of radar, the radar wave. I do this all very quickly because we can spend a whole master study on this topic. And so we make use of the phase, and the phase changes over time, as you can see here in this little graph. And that is an indication of the changes in indication of deformation or uplift. And here you get a more technical one. So radar image consists of an amplitude and of a phase. And we use then image A and image B. We cut off the amplitude information. We use the phase. We convert it into an interferogram. And in the end, we convert those into time series. And here's an example of time series. So 1 point is a time series that consists of 106 measurements in this case. It gives an indication of 28 millimeters per year on average displacement over the period of 2 years. It's just an example, but this is in a few sheets how we convert radar imagery into GPS-like time series. Now, today we're talking about climate change, and while sea level is rising, what's happening on the inside? This is what I would like to look deeper into. So first of all, there's large-scale subsidence in river deltas, and for the sake of comparison, I have some material for the Netherlands and for Yangon. And I would like to start, what they both have in common is that they are a delta. And so I like to start with a situation in the Netherlands where we are based. So we built a climate impact map where you can find the subsidence in the Netherlands. There's all kinds of extra layers in here. But what is interesting, it's an open map, it's open data. You can see the internet address. It's in Dutch. I think there's also some English titles in here. There's all kinds of details in here. And what it brings is also a general understanding of the Netherlands is going down at different speed. And there's much more detail to it. And also that mining has an impact on our country, because in the very north where you see the subsidence ball, that has to do with gas extraction. And in the south, you see this blue rim that has to do with former mining activities that were stopped 20 years ago. And then this delta area all along the coast, there's a lot going on. So one of the things we did is we converted this into something on, again, high level stability index ranking. Slides don't move.
Patrick, I think your slides are not moving.
No. Let me stop sharing.
Can you try one more time?
I'm trying. Let me go back here. Yes. So this was the subsidence map of the Netherlands that I was talking about. It's an open address, and here you can see the subsidence bowl in the north, and you can see on the coastal line that there's a lot of uneven subsidence going on. Yes. So here, the stability index, what we did here is we made a ranking of municipalities or counties, and we did it very simple on an average of subsidence rate. But this is a first step to bring awareness to what's going on. Of course, these municipalities have themselves lots of information, but nevertheless, it's a first step to make to prioritize your work. So in this sheet, you see an example where we go deeper into with INSAR, and we produced a map of subsidence to identify, and this also relates to Mr. Velrazu in the beginning for the underground tanks. Where should we build underground tanks? So if some parts of a city are going down faster than others, how does it come and what do we need to do? And so here you see two photos, two clippings, one of rainfall issues that the water no longer goes away. And the other one is of our historical buildings, in this case, a quay wall, that are suffering from all these changes as well. So here is an example of a study we did for the municipality of Amsterdam, where we made a dashboard risk indicator for buildings. You see here a little photo of the historical buildings. They're all built on wooden pole foundations. It goes back 100, 200, 300, 400 years. And so the climate change is changing the groundwater level. It's changing the growth of bacteria. And so these historical monuments, they are suffering from severe deterioration. And in order to find out the scale of it, one of the ways to use it is INSAR, is by satellites, and identify the subsidence of the buildings over the years in shorter and longer periods. And here you see an example of a dashboard that we made. This is another example of where we are analyzing based on ground level and then using proxies for the underground infrastructure. So here we identify the subsidence impact on sewage infrastructure. And we have a very good system for sewage, goes back 100, 150 years now. And so in order to help the municipalities, governments, we do this kind of analysis. And it tells you in this study also on replacements where to prioritize. So under the assumption that budgets are restricted, you need to find the spots that are worse to go to, and this is a way to identify them. These are other examples of rail. So you see here like the highway, and above it is a thinner line, whereas the rail tracks. And we are collaborating with the infrastructure owner to identify spots where our weak soil is giving uneven subsidence to the train tracks, and it helps them to identify spots to uplift the tracks, to prioritize and to stabilize the underground for future expansion. Let's go to a large-scale subsidence in Yangon. So leave the Netherlands. And here, INSAR Analytics, can we see what is going on? So in Yangon, we did this in collaboration with RVO, which is a governmental organization collaborating with the Department of Economic Development and Development Support for other countries. So here we identified a very uneven distributed subsidence over a period of years. And we were trying to find out what's going on. Now, first of all, if you look at the purple selected point at the worst in the subsidence bowl, more or less the middle of it, you find that over the period, so this is a period of 2 years, there's minus 43 millimeters, so 43 millimeters annually on displacement, which is very severe. And we were trying to find out some reasons. So one of the things we did is we added a geology map for extra context. And you can see that there's a variety of underground going on. And this is, of course, in the subsidence bowl is in a certain geological area concentrated. We added also a digital elevation model, so how the Earth currently looks like. And we identified that the largest displacements are indeed taking place in low areas. And last but not least, you see all the dots here, they represent tube wells. And it's not so surprising that in this subsidence bowl, there is a lot of at least known water extraction taking place. And so these are examples where this information can help policymakers in both giving out licenses or finding illegal water extraction. And it is, in the case of Yangon, information that they were not earlier having access to, so they can go back in a historical period, 2-3 years, This is all based on Sentinel-1 open data provided by the ESA. And last but not least, I want to take a quick look at the SAT for Flood project. It's a development of an innovative tool in collaboration with the ESA, the European Space Agency. And on a technical hand, in the analysis, we're making use of soil moisture data, Sentinel-2, and subsidence data, Sentinel-1. We did quite an extensive study of 20 or more objects. I'm focusing here today on the Edenfield Dam in Michigan, USA. This is a satellite image after the dam broke. Well, 2,500 homes damaged, destroyed. For individual owners, a nightmare, of course, compared to Mumbai, still a small amount. But also the damage estimated at $175 million. There is a movie which I cannot display because the technology doesn't allow me, but if people have an interest to see the actual collapse taking place, you can look on YouTube on the Edenfield Dam in Michigan. So I'm going to show a few slides. And what you see here is a combination of soil moisture and analysis and later on subsidence analysis. And so what we see here with the red circle is we see a seepage of moisture behind the dam in the winter from 2019 to 20. You can see also in the graph that there's sort of an uplift, assuming that the soil moisture is increasing. In September, so before that, we see also that part of the dam is near saturation. So this is another interesting observation. This is all, I have to admit, in hindsight, so we never did this as a monitoring project, but in hindsight, this was all detectable. Another element that we look into is that we believe that if you look at the disruption in the even grass pattern, that groundworks were to have taken place at this location, and it's well known that if groundworks take place, it's either an indication that something is wrong and or you change some of the layers or the structure of the dam, we don't know. But at least it's visible. And here, this is in May 12, the same spot where the groundworks took place earlier and where we saw also a saturation, is getting saturated again. And then we look at INSAR, at subsidence or uplift. And here we see it's a very uneven pattern, but we see something which is called bulging swelling taking place starting in August 2018. And here, this is all after it, you see the event after the collapse. The reason I'm showing you all these images is satellites allow you to get better information on a number of water defense structures and reservoir dams. They allow you to better understand the underground infrastructure, and they can support you in policies for land development. Decision-making processes can benefit from this kind of satellite information. And this is where I end my presentation. Thank you very much.
Patrick, we have a question for you from one of the teams at MCGM. I don't know if we have an immediate answer for this. The question is, what would be the cost of preparing a subsidence map for a city like Mumbai with roughly around 437 square kilometers, sorry?
Yes. I think in map, it depends all. So a map can be done for a very small amount of a few, let's say something between 25 and 40,000 euros, dollars. I think it all depends on what you really want, the purpose and what you want to do with it. So it's okay to quote prices here over the internet, but I think the real issue is you make a map for a certain purpose, and this context is very relevant. And so when we did this work with RVO, we had a specific request to identify what was going on. And so this context determines in the end, the quality of the result and the price. But I can say that there is the price barrier to do a map like this is not so high anymore. And I can only encourage to take this into your system and make funds available for this kind of information.
Thanks, Patrick, for this. I'm sure the concerned person would, take that in their planning thing. So this brings us to the last presentation for this workshop today. And for that, now I would like to invite Michael van der Meulen. He's from the Geological Survey of the Netherlands. And his presentation is on understanding subsidence by disentangling its causes. Over to you, Michael.
Thank you very much. I hope you all can hear me. Yes, I'm Michiel van der Meulen. I work for TNO, which is a large technology and research organization in the Netherlands, and the Geological Survey of the Netherlands, which is basically the little sister of the Indian Geological Survey, is part of that larger organization. So, as the last speaker on the subject of subsidence, the first statement I would like to make is that in the bigger scheme of things, you could say that coastal subsidence is something that aggravates the problem of sea level rise. The sea is coming up, and if your lands are going down at the same time, you basically have two problems with a bigger result. And this is a rather interesting graph prepared by Gilles Erkers of the Deltares Institute. It shows here in a red line gradually rising sea levels, and it shows for a number of coastal cities subsidence that has been going on since the year 1900. We are in the Netherlands on this fairly flat green line. That may not seem very dramatic, but you must bear in mind that we have been subsiding for a much longer period. So you could think of this line as being in a much lower position already. We have had meters of subsidence in the western soggy parts of our country. And in comparison, you see much faster and more dramatic subsidence going on in cities over the world. And the photos here show, for example, Jakarta, where subsidence and flooding are such a problem that the rather drastic decision has been taken to move the capital of Indonesia to another island. And another interesting example in Europe would be Venice, with a very beautiful cultural assets, which is slowly subsiding. And well, this is not what you would like to see, such a beautiful church and somebody canoeing in front of it. And by comparison, this image of Gouda in the Netherlands seems not very dramatic, but you can see that the water level is rather close to the street level. Yes, water levels in the Netherlands are managed, but if we lower the level here, then basically we would affect the stability of the houses that are standing next to it. So what you must bear in mind is that coastal subsidence or subsidence in this type of environment is something that is often caused by people, and it is of course caused by geology, as also already mentioned by the previous speaker. And the last curve I would like to point your attention to is that of Tokyo, which has been going down considerably since for a century, since 1900. But at some point in time it stopped, and what stopped was basically the pumping of water. So there were the conditions that allowed for subsidence to occur. There was human action that actually caused it, and when they stopped it, the subsidence stopped as well. So to the next one. So coastal subsidence is often a matter of human action, and you must think about draining soils may result in subsidence. Pumping water may result in subsidence, but also various mining activities, for example, pumping up gas or oil or salt mining or any type of mining may result in subsidence. And it does not only result in flood risk, but you can also have damage in the built environment. Here is the notorious example of the city of Bergen in Norway, where you see that these houses are rather crooked because of differential subsidence, much in the same way, occurring much in the same way as illustrated by the previous speaker. So let's have a look at the Netherlands. Subsidence is a problem that we have, but I would say it is a bit of a disguised problem, because our lowlands are going down, but they're so well protected that you can't actually see and experience it very well. But we have been going down, we are going down at rates up to 2 centimeters per year. Some of the lowest areas are almost 7 meters below sea level. But as I said, as we are fairly well protected against floods, the fact that it is actually not very comfortable to live so low relative to the sea, well, it is not very apparent. Thing is that subsidence will continue, and in the Netherlands that is primarily due to 2 processes. One is the drainage of our clayey and peaty soils, which will compact if you drain them, and peat will even oxidize and simply disappear if you drain it. So basically the shallow subsurface gets to be smaller if you extract the water, and that expresses itself as subsidence. But also we are producing a variety of resources from the deeper subsurface. Gas in the north of the country, which resulted in this red circle in various maps that were shown previously. Basically the lands there will go down for up to ½ a meter, which may not seem a lot, but this was territory that was already low. We will be stopping large-scale production of natural gas, but there will be new uses of the subsurface that may and probably will be accompanied by subsidence. So this is subsidence is something that we need to give our attention to. Well, the monitoring is quite well covered. We have this INSAR data, which are very useful next to the more traditional leveling data that are acquired with relatively old-fashioned geodetic methods. But these allow you to see subsidence, but then you need to understand why subsidence occurs. So, and as you can see from the example of the Netherlands, we have various causes for subsidence that all express themselves as the surface going down. But if you can only do something against it, if you know why it happens, and there's always a geological factor that plays a role, and then there is the human interaction with geology that plays a role. And if subsidence is caused by people, you may solve that problem. You may address that by, well, you basically manage the cause of subsidence. You can make decisions about draining or even about hydrocarbon production. And if that doesn't work for some reason, if it is not possible, you will have to manage the consequences of subsidence as they are expressed in water management. So if you want to work on subsidence, well, data is everything. And as the Geological Survey of the Netherlands, we are lucky enough to be the host of many types of data that are relevant to this particular problem. So we know the geology of the Netherlands in 3 dimensions very well, I would say, because there are 2 laws in place that give us access to a wealth of subsurface data on all relevant depth ranges for this particular problem. So we know where the easily compactable soils are because we have drilling information. We have models, basically 3D geological maps. And apart from that sort of information, we collect data on groundwater, but also on mining. So basically the geology and several aspects of the human interaction with geology, so water management and mining, we have data available. And next to that, we have access to all kinds of geodetic data. For example, the INSAR data that was introduced by the previous speaker. So we can see subsidence and we can explain it. And what we need to do is to translate our understanding of subsidence into models. So what we do at TNO, at the Geological Survey, is we have created various models of compaction. So we know how much the soil will compact if you drain it, as superficial deposits, for example. And we have the similar kind of understanding of the compaction of reservoirs in the deep subsurface if you produce natural gas from them. We have access to surface elevation data in a very high resolution even. So if we understand the processes of subsidence, if we are able to model them, and if they explain the subsidence that actually occurs or has occurred over a certain period in the recent past, then we can use our understanding and the models to predict. You can say something about the subsidence in the future. So calibration of models with data is a key ingredient of how we tackle subsidence and the Geological Survey, and also make scenarios or predictions, if you like, of the future. So the previous speaker showed that subsidence data is actually deformation data, comes in a very high resolution. You can see on the one hand a regional subsidence, which may be caused by geological processes and people interacting with geology. And next to that, with INSAR, you are able to see the damage to even individual buildings or infrastructure. And what we do, not alone, but also with other institutes, is we put all of this together. So we have the capability to predict subsidence. We have a grip on the factors that control it, and we can therefore even use it to predict damage to the built environment. Large-scale subsidence is something that expresses itself as a water management problem, for example, in relation to sea level rise. But on a very small scale, you can make inferences on damage to individual buildings. So basically, what I would like you to remember from this presentation is that understanding and managing subsidence, it is really a joint effort, because as already shown in the situation in the Netherlands, the data that is relevant will be scattered. Some of it may be stored by the Geological Survey, some of it is open data that is managed somewhere else. You will need data on the built environment, so there's no single institute typically that holds all of the relevant data sources. The same goes for the understanding and the models. So this is why subsidence is a subject in which we often work together with Deltares, because our expertise joins up to something that allows us to understand subsidence much better than when we would try to do that alone. So we are very good at TNO in the modeling of let's say deep-seated subsidence caused by, for example, mining, whereas at Deltares they're very good in predicting subsidence on the basis of water management. Whereas we would deliver the geology, they would contribute with the models, so it's basically a single effort, I would say. So knowledge and models are distributed as well, just as the data will be. The consequences of subsidence and the measures you can take is typically also, at least in our experience in the Netherlands, distributed over various government organizations. For example, the ones that manage water or the ones that oversee mining. So also on that level, you need to cooperate. And ultimately, subsidence in the coastal environment, in the type of environment that both our environments find themselves in, it is always an interaction between water and geology, water and subsurface, and added to that, of course, people. So in order to adequately see, predict, and manage subsidence, you really need cooperation and organization. That is something that cannot be stressed enough. Various data and information agencies will have to work together, but also knowledge institutes, such as, in our case, TNO and Deltares, and also geological surveys. But data and knowledge is not enough. You also need government in place that understands the problem of subsidence and has the ability to somehow counteract it. And in that, communication is actually a key ingredient of a successful dealing with subsidence as well. I remember one of the first times I was doing research on subsidence in the Netherlands. I was invited by one of our professors, and they said, can you make a prediction of subsidence going on in a particular area of their jurisdiction? And my answer to them was, well, we understand the processes and the physics and the geology and etc. But if you want me to predict it, I would have to predict you, who are controlling the water levels. So and it was only then that they understood fully that they had a very important role in the outcome of subsidence over, let's say, the century that they were considering. So it requires data, cooperation, institutes, knowledge, government, and most of all, a good communication between all of these actors. And just as a final remark, I've had no time to have a proper look into the geology of Mumbai, but I found this beautiful hand-drawn geological map, a couple of decades old, which shows me that you have had wetlands, sediment, etc., sitting on top of the famous Deccan Traps, of course. Well, where there are wetlands and sogginess and potential flooding, then the Dutch will feel at home. So I would be very curious to have a proper look into the geology of Mumbai and to what it might bring in terms of problems, subsidence, and also stability to the built environment. So thank you very much. I will stop sharing and give back to the moderator.
Thanks for this wonderful presentation and specifically the image at the end. We have a pretty long question for you that's come. The question is that extraction from Earth due to human activities appears to be the main cause of man-made subsidence. Then what shall be the remedies to fill such geological gaps? Once mapped, then what would be the probability of a future subsidence? Do we need to carry on mapping continuously?
Well, what you often see with geological mapping is that you need, to understand subsidence, you need to understand your geology in 3 dimensions. And it's actually a big effort. So over the relevant depth range, you need some sort of information. And you need to build that typically from boreholes and 3D modeling techniques, get a grip on that. My experience is that geological mapping is never done, not because geology changes so fast, but because data is always limited, and once you get more data, you have more insight. Actually, in case of subsidence, it is geology that is changing because people are making changes to, for example, the thickness of a layer, and it would be good to actually account for those changes in your geological model. It is typically not enough for subsidence, which is truly a 3-dimensional problem because it is rooted in the subsurface. It is not enough to just have a geological map. You need some sort of 3D insight, and that is a big job. I hope that it answers the question, otherwise you can simply...
Thanks, Michael. I think it more or less answers the question. So this brings us to the end of the workshop that we have planned today. And while we are slightly, beyond time, I would now like to invite Bart again to deliver the closing remarks for this workshop. Over to you, Bart.
Thank you, Kailash. Yes, we've run out of time. We are over time, but actually, if I see the number of participants, I think we didn't lose many. Of course, other people had appointments, but considering the quality of the presentations, I think there was enough reason for people to stay. Before I start thanking people, a few of the takeaways for me today. I think one of the main things that was highlighted by Bas, by the Professor Jonkman and Jan Pelen is that there is an end to building gray infrastructure to help to engineer you out of sea level rise and floods. So we have to revert to more, let's say, soft sea defenses and flood defenses along rivers. And like also Jan Pelen and Professor Jonkman indicated, that can sometimes bring about or be done in a way that you have cross-financing projects. So if you talk about, for instance, a parking garage in the dike or under a dune, that is a cross-finance of your sea defense. And also that goes for the boulevard in The Hague, Scheveningen, and that Jan pointed out that the parking space over there is paying for the sea defense. So that's an interesting notion, multifunctional use of sea defenses. Of course, on subsidence, the main takeaway is that it aggravates sea level rise. That's as clear as can be. But also, what is interesting, it's basically subsidence is a man-made disaster. If you keep on extracting groundwater for drinking water uses or what have you, like in the Netherlands, what we did is we created or we extracted peat as fuel, and that of course made that the whole of the land started subsiding there. So these are main takeaways, I would say. A lot of differences, of course, there are between Mumbai and the Netherlands. That's obvious, but there is also a lot of similarities. And as people have pointed out, yeah, that offers a lot of opportunity for cooperation, I would say. There are a number of technical systems that have been, and knowledge actually, that have been presented today that could be a basis for cooperation. We've of course seen the research by TU Delft and also by TNO, I would say. Supriya, Krishnani, and Bas Jonkman, they indicated a bit what TU Delft is doing on all that. Delta Flume, of course, can be very instrumental in finding solutions. We saw this example of the hill block concrete elements that could help building sea defenses in a much cheaper way than it is generally done now. And when I saw this example by Mr. Klein, it reminded me of the huge concrete tripods that you see all along the coast here, that could actually apparently be replaced, or when they have to be extended, it could be an interesting solution for those as well. So I see a lot of opportunities. Land subsidence, of course, there is analysis by TNO and SkyGeo, and of course that is very essential if you want an integrated flood protection plan for Mumbai also. But the most important takeaway, I think, actually, Mr. Velrasuga gave in the beginning, because he said there is only three things that can control the sea, which is the moon, the wind, and the Dutch. So if you want to cooperate, if you want to work on controlling the sea, also in Mumbai or in India, you know where to find us. The consulate is open for first contacts, and we can guide you to the right persons if you haven't seen them here today. Well, that brings me to the thank yous. Of course, Mr. Velrasu in the first place, thank you for taking your time, valuable time, and also for bearing with us until the end. So yeah, that is, I think, a very good signal for us. Also, the fact that you have arranged a lot of staff to attend this meeting. I hope that something beautiful grows out of this. I would like to thank all the presenters, of course. I mentioned a number of you, I think most of you actually already by name, so I'm not going to repeat that. We yeah, of course, also want to thank the participants that are here, and I hope that we gave you some food for thought, and if you want to continue on these discussions with us, you know where to find us. Last but not least, two persons I also need to thank is Priya Anil of the Consulate. Can somebody show Priya somewhere in the screen? Because she is the person to go to if you want to have, that's Priya, hi. She is the person behind this webinar, and she's the person to go to if you want to contact the CG in future. And then also, of course, a big thank you to Kailash and the SW, what is it, the Smart Waterworks organization that have been very helpful in organizing this, getting the speakers together, getting the audience together. So thank you also, Kailash, and also for moderating this session. It was very useful. Okay, and with that, I think we need to close, right? I don't know whether you wanted to say something, Kailash, in...
No, but I think, you know, you have more or less encapsulated or summarized what we achieved today. So as the host for, you know, as the country host for this, I think you should be the one doing the closing note. Thank you.
So basically, that's what I just did. So I thank you all for staying with us, for attending today and staying with us for so long. And I hope to be able to continue the discussion at a different occasion. Thanks a lot.
Thanks. Bye.
Bye-bye.
Thank you, Bart. This brings us to the end of the session today. Thank you for all the participants. Thank you.